Okay, hi everyone to this video about the fundamentals of flow equations. And the idea of this video is that you learn how fluid flows through a bed of particle. So now we consider a full bed, not only single particles, and you get a general, like really general insight into different reactor types, so very shortly. And the aim is that we derive an empirical model for the pressure drop. So there are specific models and we will talk about them in a different video, but the idea is to derive an empirical model, which is quite general, to get an idea about the pressure drop. So the fundamentals of flow equation is to relate energy input, flow behavior, and system properties, as you see here. And what this means is that flow equations are mathematical equations, and these equations describe the relationship of the energy needed for the flow. So the flow has to go through this bed, right? And it needs energy, especially when it goes upwards. Downwards there's gravity, but upwards you need to pump energy, and this energy is also related to the pressure drop of the bed. So there's a pressure drop along this bed. We will talk about this in a minute. And the achieved result is the volumetric flow rate and the flow velocity. So how much liquid or fluid goes through and how fast does it go through, and the relevant property of the bed and the fluid. So what are the material properties? What is the property of the bed itself? So porosity, for example. What is the fluid properties like viscosity and so on. And all these different things are put together in one equation to calculate, for example, at the end, the volumetric flow rate. So how much fluid you get through, or what is the energy you need. And therefore we have multiple examples, and one example we always, not always, but often use is lithium. So here you see a picture from the Atacama Desert, and from there we get lithium from brines, and at the end we get lithium carbonate. And in the process we have multiple times where we have a fluid flowing through a bed. So we have it here and here. This is sedimentation, this is filtration. So if we look at a sedimentation or thickening tank, sedimentation tank, in this area we have a very, very dense liquid. So we have packed particles, and the liquid, the fluid, the water in this case, has to go through it. So here in this region we talked about the flow or the settling in terms of Ricard-Zaki equation in another video, but here we have really a dense packing of particles, so we could consider it as a flow through a bed of particles. And the same we have in filtration. So filtration, of course, coffee is always a nice example. So we have particles here and the liquid goes through the bed of particles, and we also have the filter paper. The importance you will see when we talk later about filtration. But we have the flow of water through a bed, a packed bed, which is coffee. And of course you want to have as fast as possible your cup full with coffee, but it also has to taste like coffee. So it needs a certain time for the extraction, right? And therefore we need flow equations. So we have also reaction processes in chemical engineering, right? So there are chemical reactions, and these reactions are in different type of beds. And one type is a fixed bed. So we have a flow through a fixed bed, and the fixed bed is defined as a granular layer in which particles are arranged in a more or less random packing and remain stationary. So here we have a fixed bed. The particles are randomly oriented. There is no fixed order how they are positioned, and the fluid, as you see in this very nice GIF, runs through it, and the porosity mainly depends on the size distribution and shape. So the porosity of the bed is related to the size of the particles, the shape of the particles, but generally we say the porosity of such a bed is around 0.4. And these reactions, these reactor types, fixed bed reactors, are used, for example, in the Haber-Bosch process, or when we talk about absorbers with activated carbon. So in this case, you can consider a fixed bed and a fluid through a fixed bed. Okay? And then we have a moving bed, and in the moving bed, basically it's a fixed bed which moves but the whole bed moves, not a single particle move. The whole bed is somehow stationary or fixed, but it moves itself through the reactor. This could go upwards or this could go also downwards. For example, in reduction of iron ore in shaft furnaces, the pellets, the iron ore pellets, they fall downwards and the fluid goes upwards to decrease their velocity, and then there is a reaction to metallic iron. And also in fluid catalytic cracking, these kind of beds are used. And finally, there is what we call a fluidized bed. And when a fluid flows through a particle bed, basically a fixed bed, the bed becomes fluidized once the minimum fluidization velocity is exceeded. And the minimum fluidization velocity is exceeded when the fluid goes very fast. So the fluid goes first slow, and then the velocity increases. And at one point, the minimum fluidization velocity is exceeded. So the particles start to lift. But important, they don't leave the reactor, as you see at the end of the GIF. They lift to a certain extent, and then they move randomly in this zone, but don't follow the flow. And these kinds of beds are used for drying granular solids, for example, or to coat particles in the pharmaceutical industry. So when we think about reactions of a fluid with solids, we have these three types of bed: fixed bed, moving bed, fluidized bed. So, and what I would like to do now is to relate the flow resistance and the pressure drop. So when a fluid flows through a bed of particles, as we saw in these three types of reactors, for example, it feels a resistant, and this resistant leads to the pressure drop. And the pressure drop basically is the magic question in these flow equations. So, because there is friction, right, of the fluid with the particles, and this is basically the resistance the fluid feels, and this is at the end the pressure drop. So, since the particle bed represents a highly heterogeneous pore system whose internal geometry, the size of the pores, the shape of the pores, is determined by particle size and shape distribution, packing stage, so how compressed everything is, and mixing, it constitutes a highly complex flow phenomenon that requires substantial simplification for modeling. So to keep it short, to describe the flow through a bed of particles is too complicated. Okay? So we need simplification because of the different sizes and the pores, the shape of the pores, the packing, the porosity, how it's mixed, and all these things, so many influencing factors, very, very complicated. So we need to simplify it. And to illustrate the essential interrelationships, an empirical model approach will be presented now. So at the end, we will try to make a simplified equation which gives us an idea how these different properties are related to the pressure drop. Okay? To calculate the pressure drop, or if we know the pressure drop, we can get an idea of the packing or of the porosity or whatever. But this relation should be illustrated in a simplified empirical model. So we keep it really simple. So we have this picture here, and this means we have a flow going in, and here we have a bed of particles, and now we don't know much about it, and this is why you see just these diamond shape pattern. So, but we know is we have a pressure here and the pressure here. This pressure is higher than this pressure. Our bed has a certain length, it has a certain velocity, and the fluid has an inflow velocity, but in the bed we have a velocity in the pore system, and this is different to the velocity here, right? And then we have a viscosity, and we have also a cross-sectional area of the bed. If we look from this view, we would see an area here, okay? And what we generally assume for this gray area here is a fixed bed with homogeneous random packing. Okay, so the most simple we can do, because then we know the porosity, then we know fixed bed, nothing is moving, so it's the easiest way, and we want to derive an equation for the pressure drop delta P, so P1 minus P2. So how much energy do we lose? What is the pressure drop along the bed? And therefore we can say that the pressure drop, and the pressure drop is often related to the length, and then we have, because then we make it independent of the length. I mean, you could also make it dependent on the length, and it goes here. But in this case, it's very often, as in most equations you see, the pressure drop divided by the length of the bed, which is mainly known. And this is a function, of course, of the velocity of the fluid in the bed, okay? And it's also a function of dH, and dH is the average hydrodynamic pore diameter. And this is an assumption where we say we have small pipes. And in these small pipes, the liquid goes straight through. And this is basically what we know from fluid mechanics. So we have the simplification that our porous bed has pipes and the liquid goes through these pipes, and at the end it leaves the pipe and comes out again. Then we have a porosity. The porosity, of course, influences the pressure drop, and we have a viscosity, right? The viscosity of the fluid, of course, also has is paying into the pressure drop, and the density of the fluid. The density of the particle is not really important, the density of the particle. So all these variables are important to describe the pressure drop, okay? So, but we would like to simplify the variables a little bit, and therefore we can say there is a relation between the inflow velocity and the average fluid pore velocity. So the inflow velocity is very easy to measure. The velocity in the pores is not so easy to measure, but the inflow velocity divided by the porosity gives the fluid pore velocity. So a high porosity means there are a lot of voids. And this means there's a lot of space where the fluid can go, and this means it can go rather slow through it. But if the porosity is very low, the gaps are very small. So the fluid has to go very, very fast through it, right? If not, we would lose volume flow. So this is the relation we can say for inflow velocity to average fluid pore velocity over the porosity. And there is a second relation, and this is that we said we have this idea of hydraulic diameter, which is the concept of pipe flow, and this is an extreme strong assumption with a lot of limitations, because it assumes straight channels, which we normally don't have in a fixed bed, and a constant wall shear stress, which is also not the case for our fixed bed. And as I said, these assumptions do not account for a pore system, and there is a relation between the hydraulic diameter, dH, in a pipe and the Sauter diameter. And the Sauter diameter is the diameter which basically is related to the specific surface area, right? So if you look in the video about particle sizes, the Sauter diameter is mainly measured by adsorption, so via the specific surface area. So we can relate the hydrodynamic diameter to the Sauter diameter, which is a particle size, and both are related over the specific surface area. And this is basically the expression, how they are related. So instead of dH, we can write this here. So, and this means at the end, if we look at our general equation, we have the pressure drop over divided by the length. So the pressure drop per length, and now we can replace these two first variables with two much easier variables. This is the size of the particles in the bed, easy to measure, and this is the inflow velocity of the fluid, easy to measure. Okay. So now we can make use of something we learned earlier, and this is the fluid phenomena for single particles, because in single particles there's also friction, right? And we learned that, or resistance, right, in terms of drag. And we learned that this drag or resistance has two terms. And these two terms is a friction term, and the friction term was related to or proportional to the velocity and the viscosity. And there was a pressure term, and this was proportional to velocity square and the density of the fluid, right? So if you need to to remember about this, look please in the video about drag force. Okay, in drag force we derive this and explain why there's a friction term and there's a pressure term. But if this is the case, we can say the same for our flow equation, because then we can say that the delta P divided by L is equal to a fitting parameter and another fitting parameter, but these two terms, right? So we have a friction term. This is viscosity and velocity, plus a pressure term, density of the fluid, viscosity square. And if we have measurement data from an experiment and we know these variables, we can get from the fitting K1 and K2 with these two dashes. Okay. And now we can include the size of the particle, because we agreed, or I don't know if you agree, but we said that delta P depends on the size of the particle. And this is the relation of delta P, and this is known also from experiments. So in the friction term, the relation is 1 divided by d square, and in the pressure term, the relation is 1 divided by d, and this we can add in the equation. So this is not, achieved by experiments, known from experiments. So we can say this quite sure, that the relation delta P equals 1 divided by d squared plus 1 divided by d for friction and for pressure. And since now we have considered the particle size here, our fitting parameter changes also, because the influence of the particle size here is within this parameter. But now we have it in the equation as a individual variable, and now the fitting parameter of course cannot be the same. If at the end here the number would be the same here and here, but we get an additional variable here, this parameter has to change. And now we can make a last consideration, and this is the dependency on the porosity, and this was extensively investigated and it's quite complex, so there's no general solution, but very often what is used known from experiment is what you see here. So, and this is for the friction part, is 1 minus porosity square divided by porosity cube, and 1 minus porosity divided by porosity cube for the pressure term. Okay, again, this is achieved from experiments. And now again, the fitting parameter has to change for K1 and K2 because we have much more information. But now you see that slowly this equation gets a shape. And now we can, I don't know if it's simplifying the equation, but we can go a step further. And the step further would be that we're introducing a drag coefficient, CD, right, as a function of Reynolds. But now it's for a bed, not for a single particle, so it's called lambda. Lambda is a function of the Reynolds numbers in the same way as the drag coefficient for a single particle is a function of the Reynolds number. And with this drag coefficient, the full equation gets much simplified to this shape. So now there is no friction and pressure. There is friction and pressure because in the lambda we have K1 and K2, but if lambda has this shape with the Reynolds number, the full equation strongly simplifies, especially if you know this number, right? And then we have a very nice simple equation here with the where the pressure drop is dependent on the density of the fluid, the velocity, the size of the particle, and the porosity of the bed. And for this equation, Ergun found in a flow regime between 0.4 Reynolds 1000 solution. And the solution he found in experiments, as you see here, is that K1 is 150 and K2 is 1.75. And in this way we have a quite easy equation, because now if we know all the variables, we can calculate the pressure drop of our fixed bed. Okay, so I have some tasks for you to repeat because I think it's theoretically a heavy video. So the first is that how do we derive a flow equation? So try to repeat it for yourself. Derive the flow equation step by step. Take the video as help. Try to understand what we do, why we do it, and what's the general logic of this derivation. And then we have a specific task. So we have a shaft furnace, contains iron ore pellets forming a moving bed of height h, 10 meters, and a cross-sectional area of 1 meter square. The gas, reducing gas, mainly CO8 CO and hydrogen, it's a mixture, flows upwards at a superficial velocity of 0.2 meters per second. Estimate the pressure drop across the bed using the Ergun equation for the flow through PET bags. So here are the numbers, and this is a very simple exercise to just apply the Ergun equation we derived. And with this, I hope you learned how fluid flows through a bed of particles. You get a general insight into different kind of reactors, right? Fixed bed, moving bed, and fluidized bed, and then quite much longer, or the strongest part in the video was to derive an empirical model for the pressure drop, where you hopefully got an insight. So with this, I would thank you for watching the video, and if you have any questions, please let me know.